Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to the Fundamental Theorem of Calculus. If you've been following my videos, you have found out that we have been doing the area under a curve, and we've been talking about derivatives as the opposite of integration. And integration is the opposite of derivatives. But it's been a very, very time-consuming summation process with all the summation rules and this weird little formula thing to find the limit as your rectangles approach infinite number of rectangles to get the best area under the curve. So obviously, mathematicians had to come up with a better way, right? So enter the fundamental theorem of calculus. So here we go. Let the derivative of x equal, or the derivative of g, right? Equal f of x equal the limit as h approaches 0, a g of x plus h minus g of x over h, which is what we called the derivative process in the first place, right? Okay. Then, assuming f of x is continuous and smooth, on your interval to a to b. So that continuous and smooth has been a running theme throughout our calculus stuff, and it's really, really important. So g of x, notice I've lost the prime sign here, right? G of x is going to be the integral from a to b, or a to x actually, f of t dt, for a is less than or equal to x, which is less than or equal to b. Okay, so blah, 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 right? Here we go. Simply put, basically we're saying that an interval from a to b of f of x dx, which we've been turning into all these rectangles, is going to equal capital F of b minus capital F of a. So therefore, how does that look? Now this is a definite interval because we have lower bound and upper bound. Okay, so it's a definite interval. So let's look at this. We have the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Okay, so first of all, this is not smooth and continuous, okay? I don't know if you guys remember your absolute value graphs. If we were to graph this thing, we can see that it has a v. Let me check that window out. -5. We'll go -5 to 5. Let me turn the brightness up on this a little. There we go. So we're supposed to be going from 0 to 2, but we see it's smooth. Well, it's continuous, but it's not smooth. See that abrupt change right here? That's happening at 1/2. So what we can do, though, is we can do the integral from 0 to 1/2 of negative 2x minus 1 dx plus the integral from 1/2 to 2x minus 1 dx. So what I've done here is I've broken it up into two lines, and lines are smooth and continuous, whereas absolute values are not. And then we're just going to add those together. Okay, so now we have to think about how do we antiderive, right? So the integration from 0 to 1/2 of negative 2x plus 1 dx plus the integral of 2x minus 1 dx. Again, that's 1/2 to 2. So if you remember, we're going to add that exponent. So Negative 2 will become x squared divided by 2 plus 1 to the x, technically plus c, right? And this is between 0 and 1/2. What this rule up here said is I can just do f of v minus f of a. Okay, so negative 2, well, let's just go ahead and reduce that, right? So negative 1/2 squared plus 1 times 1/2 plus c minus negative 0 squared plus 1 times 0 plus c. So here we'll get negative 1/4 plus 1/2 plus c minus c. So see how the c's will cancel? Okay, negative 1/4 plus 1/2 is 1/4. So we're getting 1/4 from the first one. All right. Plus, integrate this. So we would have 2x squared over 2 minus 1x plus c. And that's from 1/2 to 2. We'll go ahead and reduce that as well. So we would have 2 squared minus 2 plus c minus 1/2 squared minus 1/2 plus c. So 4 minus 2 is 2, so we'd have 2 plus c minus 1/4 minus 1/2, whoops, plus c, forgot that for a second. So 2 plus c, this would be negative 1/4, but this minus would make it plus 1/4, and we'd have minus c because the negative would distribute through. So it looks like we have these c's canceling out again. So the 1/4 from the first one plus the 2 1/4 from the second one gives us an overall area under the curve of 2.5. And if you noticed, all the plus c's ended up canceling out. So let's look at that as an actual area, okay? So 1, 2. At 1/2, it's at 0. At 0, it's at 1. And at 2, it's at 3. So if we think about it geometrically, we've got this triangle. It's a base of 1/2 and a height of 1. So base times height divided by 2 is 1/4. And here, we have a height of 3 and a base of 1.5. So if you do base times height divided by 2, you get 2 1/4, which still gives us 2 1/2. So in this case, we were able to justify the area geometrically as well as utilizing integration or calculus. But you'll notice that the plus c canceled out each time. And so for that matter, with definite integrals, when you have an upper and lower bound, you can kind of shorthand it and cheat the plus c out. All right, so, and also the other thing is these you can check with your calculator because they have an upper and lower bounds. So 0 to 2 of 2x squared minus 3x plus 2 dx. Now think about this. This is a parabola, right? We're trying to find the area under that curve. That's what we're looking for. Okay, so what we're going to do is we're going to integrate it. So this would be 2x cubed over 3 minus 3x squared over 2 plus 2x. Technically still plus c, right? And we're supposed to do the upper bound minus the lower bound. So 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 2 plus c. There's substituting 2 minus, when we substitute 0 into all of this, we just get c, right? Okay, so 16/3 minus 4 12/2, which is 6, plus 4, and the c's will cancel. Okay, right? Negative 6 plus 4 is negative 2, and 16/3 minus 2, which would be 6/3, is 10/3. Let's check it in our calculator. So go into our math function. We're going to come to integration number 9. We're going from 0 to 2 of 2x squared minus 3x plus 2 dx. 3.3 repeating, or 10/3, which I still have my thing in here from the last video I made where we did everything with areas. So this is definitely much faster and simpler than actually trying to do all the area rules. So we definitely do need to make sure that we understand a couple of the integration rules. And I will be making a video on all those little bitty integration rules. So if you don't understand that, make sure that you go and you double check that video out. Just hadn't got around to posting it yet. Right now we're just kind of working off your memory. So if you didn't understand where some of that stuff I got in was, I'm using a couple books together to go ahead and come up with some of these videos, examples, and sometimes I just like one book more than the other, and we're just getting this one today. So if you get an integration like this one, negative pi over 3 to pi over 3 of 4 secant theta tangent theta d theta. This one really kind of makes you think about your memory, and remember that we can pull this 4 out to the front. And secant tangent, if you recall, when you got that answer because you derived secant. So the integration goes back to just plain old secant. I'm going to stop writing the plus c because I know it's going to cancel out. And negative pi over 3 to pi over 3. Okay. So let's think about pi over 3. If you remember, that's 60 degrees, right? Okay, so cross 1, 2, square root of 3. So secant's a reciprocal of cosine. So cosine would be 1/2. So secant is 2 over 1. So 4 times 2. All right, and if I do negative pi over 3, put my 60 there, even though I drew a bad triangle here. 1, 2, square root of 3. It's the same thing. So I'm getting a net area of 0. Why is that? Well, make sure you're in radians. 4 tangent theta divided by, multiplying by secant is the same thing as dividing by cosine. Okay, and this looks really weird, right? So now let's just go ahead and change our window from negative pi over 2 to positive pi over 2. Okay, so we'll make it even taller. Make sure we can see this. Do you see how this area and this area is the same, and they're kind of canceling each other out? That's why we're getting a net area of 0, is because what's under the curve and what's above the curve are equaling out to the same thing, so we're getting a net area of 0. Okay, so big idea. Anytime you see this, it means you're calculating the area under a curve. Okay, now, I just realized that I'm very monochromatic today. We'll switch it up a little bit because here's the deal. We're going to do the second fundamental theorem of calculus. I know, we wait all this time to do the fundamental theorem of calculus, which is to give you what a definite integral is. Then we add in the second fundamental theorem of calculus too. The second fundamental theorem. Okay, if g of x, notice the capitalization there, equals the integration from a to x f of t dt. Now notice these are both t's, these are both x's. Okay, that's very important. Find g prime. Okay. So find the derivative of g, which is the integration of f. Okay. We're going to go ahead and we're going to work it out completely, and then we're going to come back and kind of talk about what's really going on here. So g of x equals the integral from 4 to x cubed of 2t plus 1 dt. Find the derivative of g. Okay, well, first of all, I need to work out what g really is. So let's integrate this. 2t squared divided by 2 plus 1t plus c. Okay, applying that fundamental rule of calculus. So now I've got to put in x cubed, so that would give me x to the 6 plus x cubed plus c minus 16 plus 4 plus c. So again, the c's will cancel. So g of x equals x to the 6 plus x cubed minus 20. So the derivative of g is 6x to the 5th plus 3x squared, or 3x squared multiplied by 2x cubed plus 1. Now, the second fundamental theorem of calculus says that I can go from here to here without all the in-between steps. Why is that? Well, deriving and integrating undo each other, kind of like multiplying and dividing undo each other. So if you notice, instead of t, I have x cubed inside of my parenthesis. And instead of dt, I have the derivative of x cubed right here. That's the second fundamental theorem of calculus. It says if you're going to integrate and then rederive, kind of a switcheroo on variables, where your base number is a, it's important to know that we need a number. Like here we had a number 4. Okay? So sometimes you'll even see it written like this. d dx, integral of 4 to x cubed, 2t plus 1 dt. It's the same question I asked, just a lot shorter, right? Instead of writing all that, I kind of shortened it up. So these are going to cancel each other out, basically. We're dropping that in there, and its derivative in there. So 2x cubed plus 1 for the t, and the dt would be 3x squared. Boom, done. Okay? That's the second fundamental theorem of calculus. I didn't write it out completely formula, but that's all we have to do. Now, some people will ask rules about, like, well, what if it's, you know, this, or what if it's that, or can we turn things into a second fundamental theorem? Yes, but generally, if you have the second fundamental theorem of calculus, you're going to have a variable for your upper bounds. If not, I've had this question. What if I have 9 to x and versus this? Well, normally we do f of b minus f of a. Well, if here you do f of b minus f of a, think about your subtracting. See, that's just changing signs. So this will equal -1 times. Then they would be equivalent statements. So that's one way that you can switch it, because it just switches that subtracting order, and we know anything that time we switch subtracting orders, it changes the sign, like 9 minus 2 and 2 minus 9. They're both they have the same absolute value, just one's positive, one's negative. So there's your fundamental theorem of algebra and your second fundamental theorem of algebra. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.